Moving on in question 1, we're now dealing with magnesium oxide used in batteries, and we're given a galvanic cell diagram or a battery diagram, as well as a data table of standard reduction potentials. So where you see these E values in volts, this is called your standard reduction potential. And you'll notice that on this chart, all of these half reactions are written as reductions, which is gaining electrons. So some of these reduction reactions, actually only one of them, this one is spontaneous because I have a positive reduction potential. And these first two half reactions, these two are non-spontaneous because you have negative standard reduction potentials, meaning that I need 0.76 volts to reduce equation 1, and I would need 1.28 volts to reduce equation 2. So because my equations 1 and 2 have negative voltages, I know that one of these is going to be the oxidized portion of my half reaction, or also known as the anode. So when I'm going to write the balanced Net-Ionic equation, the one that will be the most favorable, well, I already know that my cathode and my reduction, so my reduction, red cat, is going to be 2MnO2, because remember, this is the only choice I have for the reduction. This is the only one that gets spontaneously reduced because of its positive E value. All right, now when I choose my anode or oxidation, red cat anox, I'm going to choose the one that will give me the greatest voltage. And so that's going to be equation number 2. So I'll show you the formula for this when we answer part 2, but I'm going to choose this one because when I look at this combination of redox reactions, that will give me a greater overall potential or overall voltage than if I choose equation 1. So just be careful, okay? When you copy this down, you have to flip the equation because, like I said, it's written as a reduction. We have to make it an oxidation by making it lose electrons by flipping it. Okay, so bear with me as I write this down. Okay, now that we have our two half reactions, we can add them up. And remember, when you do the Net-Ionic, if you have a reactant and product and it did not change, it will not be part of your net equation because it did not change from reactant to product. So there's no difference. It didn't really do anything. So for example, water is a spectator. It's a reactant here and a product here. So it did not change forms. Your electrons also will be canceled out of your net equation. And then I've got a hydroxide, 2 hydroxides here as a product, 2 hydroxides as a reactant. So they did not change form. So my Net-Ionic equation will be 2MnO2 solid plus zinc produces zinc oxide solid and manganese oxide. All right, now let's calculate the Ecell for this overall redox reaction. There's a few formulas out there. I like to use this one. Ecell equals E cathode plus E anode. But we have to flip the sign. And what I mean by that is, okay, let me clean up the data table a little bit. What I mean by flipping the sign, well, let's copy down the cathode first because we know that the reduction or the cathode has a voltage of 0.15 or a standard reduction potential of that. And then the anode, so again, this is my reduction, right? So when it's reduced, it will be negative 1.28 volts, meaning that it will need 1.28 volts to be reduced. The reduction would be non-spontaneous. So I'm going to flip, and that's what I did in my overall Net-Ionic equation. We change this to an oxidation by flipping the equation. So I also need to flip the sign, meaning that when I oxidize it, it'll generate 1.28 volts. And overall, my Ecell is a positive 1.43 volts. So this battery is generating this many volts. And that's what a battery is supposed to do, right? It's supposed to be the spontaneous redox reaction that generates energy. Okay, moving on, calculate delta G in kilojoules per mole. Remember, delta G, when it's negative, it will be a spontaneous reaction. In this case, we're dealing with redox, so I have to use the Nernst equation to solve delta G, which is negative NFE. By the way, E is what I just calculated, that's this. F stands for Faraday's constant, and then N refers to the moles of electrons. So in this calculation, I'm going to have negative 2 moles of electrons times Faraday's constant, which is 96,485 coulombs per mole. So what I see right away is that moles will cancel out with moles. I have to be careful here because the question asked me to calculate it in kilojoules per mole, but right now my E value is in volts. So there is a conversion factor that 1 volt also equals 1 joule per 1 coulomb. So for example, like this 1.43 volts, it's also equivalent to 1.43 joules per coulomb. So I'm going to need that to get coulombs to cancel out. So I'm going to include that in my calculation here. So I'm going to change the volts to joules per coulomb. But now, as you know, in this question, it says here kilojoules per mole. So let's change joules to kilojoules. Now, there are 1,000 joules in 1 kilojoule. So I want joules to cancel out. I'm going to make a ratio here where joules is on the bottom, so this cancels out. Kilojoules is on the numerator, so that's the answer I'm going to get. And I know that for every 1 kilojoule, there's 1,000 joules. So when you do this math, your answer will be in kilojoules. And the answer I get will be negative, and we're going to round it to 3 significant digits, 276 kilojoules per mole. Okay, now the mole, sorry, if I go back to the electrons, it's 2 moles of electrons per 1 mole of the entire reaction. So my answer will be expressed in kilojoules per mole. So again, the negative value of your delta G means, yes, this is actually a spontaneous redox reaction. Gibbs free energy is being released. And I can tell that from this positive Ecell value as well. Last question here on number 1. A student claims that the total mass of the alkaline battery decreases as the battery operates because the anode loses mass. Do you agree or disagree with the student's claim? And justify your answer. So this is a little bit tricky because the anode it depends on the type of galvanic cell, but typically when I have, let's say, a metal in its own like aqueous metal solution. So for example, if zinc was, I'm just going to draw like this, this is solid, and then if it's sitting in a solution of, let's say, zinc ions aqueous, this will oxidize into zinc 2+ and 2 electrons. So over time, if this was my anode, the anode part would lose mass, but will the total mass of the battery decrease in this case? I don't think so, because actually there's a hint in the diagram up here. So if you look at this battery diagram, this whole thing is encapsulated in a closed system, right? It's boxed up into this casing. So even though if your anode is losing mass, it's not going to change the mass of the whole system because nothing's really escaping to the surrounding or to the atmosphere. So we're going to say here no, disagree, because we have a closed system. Which means that there is you guys also know from probably equilibrium that when you have a closed system, the mass cannot change because nothing is actually escaping that closed system. So because the battery is closed, mass cannot escape the battery. So the overall mass will remain the same. Hopefully that makes sense. Please leave any questions you have in the comments, and thank you for watching this part of the video.